So in this video, I will talk about the second derivative and concavity. We will try to get the answer to the question, what does second derivative say about a function? And what we have? We can see here two graphs. Both of them, function f and function g, are increasing, but they look a little bit different. At the moment, we can say they are bended like in different direction. But let's investigate like what kind of characteristic the second derivative will give us for this different directions, the different like bend. I have the same function f and function g, and of course, our really good tool is a tangent line, the slope of the tangent line. I mean, I draw a couple of tangent lines. That means this is the first tangent line, and that's the slope. This is another tangent line, and we can see that this tangent is steeper, and this one is even more steeper. That means we can say that the slope of the tangent line is increasing. Okay? And slope of the tangent line is simply the derivative. We also learned in the previous section that if derivative is positive, then original function is increasing. Okay. And now what we can say, since slope is increasing, okay, then we can say that its derivative of the slope is positive. And slope, of course, with respect to calculus, is the first derivative. That means slope, derivative of the slope is positive. Okay? That means when the curve is bended this way, is bended up, we can say that the second derivative is positive. And I believe I typed this. Slope of the tangent increases, f prime is increasing, which means derivative of that guy, which is f prime, which the result is the second derivative is positive. Oh, okay, let's wait. That means I can say one more time, second derivative is positive for this shape of the function. Now, looking at the function g and the corresponding slopes of the tangent, that's the slope of the tangent, and that's another slope, and that's another slope. And we can see the first one is steep, the next one is less steeper, and then this one is like, it's like approaching almost a horizontal line. That means the slope of the tangent line decrease. Okay, the slope of the tangent line decreases. And the same situation, if the slope is decreasing, its derivative is negative. Because if the function is decreasing, its derivative is negative. I mean, we can see this is slope. Yes, slope is decreasing, then the derivative of this must be negative. And derivative, of course, of this will be the second derivative. So for this, if the function is bounded down, okay, we can say that the second derivative is negative. Okay, that's when we have the answer to the question, what does the second derivative say about the function? And let's actually look at the proper terminology. If the function is previously said bounded up, we will actually call the proper way to say is concave upwards. Function is concave up. If the function is like bounded down, we can say concave downwards. Okay, but also let's look at the definition, because having a function, we have to be able to identify if the function is actually concave up or concave down. you can always try to draw a tangent line to the curve. And if the tangent line is placed below the curve, yeah, now I'm not investigating the slope, the rate of increasing or decreasing, no, just the position, that we can see tangent line is below the curve. This, of course, means that curve is above. That means if the tangent line is placed below the curve, this means that the curve is concave upwards. And respectively, on the other side, if the tangent line, when you draw a tangent line and tangent line is placed above the curve, then curve is below, the curve is bended downwards. Okay, and concavity test, just what we did. If the second derivative is positive, function is concave up. If the second derivative is negative, for all of the x's in the given interval, of course, then the graph of the function on that interval is concave down. Okay, we may also think about the transition points. Okay, the points that actually the function will change its concavity. Looking at this graph, you may probably notice that point B, point C, point D, point, okay, let's say E, okay, and point P. Okay, we have, because I like label all of the points, and let's see what we have. We may think that these points actually are the points where a function is changing the position from concave downwards to concave upwards, or the other way, changing concavity. And first of all, we will call these points inflection points. Okay, inflection points. And we can definitely see function is concave down, which means second derivative is negative. And then at the point B, up to point C, function is bounded up, it's concave upwards, second derivative is positive. That means definitely at the point B, second derivative changed the sign. And now, starting on the right-hand side at C, we can see that it's really gently, but function is bended down, second derivative is negative. That means also at C, second derivative is changing sign from positive to negative. And then again is positive. Okay? That means definitely point B, point C, point D are the inflection points. However, what's happened at E? At E, because point E, it's a, I would say, special number also. I can like give you some features in a minute. But what's happened with respect to the sign of the second derivative, we can definitely see that the second derivative is not changing the sign, because function is concave up, positive second derivative, and again concave up. Of course, something happened at E. We definitely know that the derivative at E, the first derivative, is undefined because we do have a corner. But talking about the second derivative, it's also positive. That means point E is definitely no, that's not an inflection point. Yeah, this is no inflection point. Okay, no inflection point because second derivative is not changing the sign. And at the point P, I believe on the right-hand side, function is bended down, second derivative is negative. This will be inflection point. Okay, that's we can see, if we have the graph, we can probably easily identify. But now the thing is, having a formula for the function, how can we find the potential candidates for the inflection points? We will take, of course, a second derivative and set up this equation. Second derivative is equal to 0. And then we will have a few points, we will solve this one. Or also the important numbers are if the second derivative is undefined. Okay, but what is the The thing is, we may solve both of these equations, and you probably recognize this for the critical points. When we were looking for the critical numbers, we were solving the first derivative. We were setting up the first derivative 0, and the first derivative is undefined. And we were solving this, checking against the domain and listing as a critical numbers. But also, the next step was to identify if these critical numbers are giving us extreme values. And we also know that not all of the critical numbers will give me local maximum or local minimum. And the same happened in this situation. We will solve this equation, we will solve this one, we will find all of the x's, and they are extremely good candidates for the inflection points. The next step, what we have to do, we have to test the sign of the second derivative on the left and the right hand side at these numbers. If the second derivative is changing the sign, function is changing concavity, and this point is an inflection point. That's probably what's happened. Point E, I would assume, because since the first derivative is undefined, I am assuming that the second derivative is also undefined. That means this will be the solution from this condition. However, testing the sign, we can see that E actually is not an inflection point. Could be the inflection point, but not in this case. Okay, and this is the summary. If the second derivative is changing the sign, we will have inflection point. And of course, we have to focus on this condition and on this condition. And definitely changing the sign at the given numbers. I mean, at the numbers x equals to c. And then we can see this will be the inflection point. Okay, that means let's take relatively easy function and let's find everything. Intervals of increase and decrease. And then looking at these intervals, of course, we will have critical numbers, and we can identify local maxima, local minima, and then concavity and inflection points. And probably we can get the graph, like the rough sketch of the graph. Okay, that's the function. Function is just the third degree polynomial. That's mean domain are all of the real numbers. No problem with the domain. For the increase and decrease and local extreme, we need the first derivative, x squared minus x minus 2. And derivative is defined everywhere. Then we don't have the situation that derivative is undefined. We have to just set up, the second derivative. Oh, okay. I mean, we will need the second derivative. Okay, that means we will just need the first derivative is 0 if x squared minus x minus 2 is 0. Actually, let me do on the top. Then we will save, we will organize our page. Okay. I know that you probably, when you're watching, you can also do it, and you can probably be faster than me, which is excellent. Okay, x squared minus x minus 2 is 0. We're looking for the critical numbers. We can factor out, I hope we can factor out 2 and 1, negative, positive. That means x equals to negative 1 and x equals to 2. That's the critical numbers because this number is in the domain and this number is in the domain. Okay, let's do test. First derivative test. Placing critical points. And I believe this will be the nice form of the derivative, and I will test the sign. If I will take a test value 3, substituting 3 to the blue box, I'm getting positive number. Substituting 0, I'm getting 1 times negative 2, negative. And substituting negative 2, we will have negative times negative, positive. Okay, now we know that function is increasing, decreasing, increasing. So we can kind of see the shape of the function. Local maximum at negative 1, local minimum at +2. Okay, we did the first derivative test and we have the answer to the question, to the part A and B. Okay, for the intervals of concavity and inflection point, we will need the second derivative, and we do have the second derivative, 2x minus 1. And the same, we will need, first of all, to find the solution for this equation, the potential candidates. Okay, that's actually not a big deal because it's just the linear equation. X equals to 1/2. It's in the domain, no problem. Okay, when I place 1/2 on the number line, and I will test the second derivative, this is the second derivative, I will just test the sign. Substituting 1, we have positive. Substituting, for example, 0, we have negative. This means that function is concave down and concave up. We will definitely have inflection point and 1/2. And kind of, if I look at here, I can say this is 1/2. Yeah, like if we will combine everything together. Okay, that's how we do the first derivative test and concavity test. And it's actually funny because concavity test is not really the second derivative test. We actually do have a second derivative test, but the second derivative test is, ironically, is still testing for the local maxima and local minima. Okay, that's what we call that the first derivative test is testing increase and decrease, increasing and decreasing intervals, and concavity we call is just the concavity test. And okay, I did place everything in one table. We can maybe fill out but we don't have to because we almost have the graph. But let's do it. This will be an interval from -infinity to -1, between -1.5, between 1/2 and 2, and from 2 to infinity. Of course, -1 and 2 was the zeros of the first derivative. 1/2 was the zero of the second derivative. And let's check the sign. Positive, negative, positive. It means function, the first derivative was positive, negative, positive. Now let's come back. Let's look at the second derivative, the concavity test. Negative on the left, positive on the right. Negative on the left, positive on the right. Okay, and now how function behaves. Function is positive, which, oh, no. Derivative, first derivative is positive, and second derivative is negative. This means that function is increasing but concave down, and then is attaining local maximum, and then again is decreasing, yes, decreasing, concave down, and at some point it's still decreasing. We know that this will be the inflection point, is still decreasing but concave up, and then attaining local minimum. Yeah, we can see, and then it's increasing, concave up. It's been kind of like we can see that this is the graph of the function. Of course, we still don't know the exact values. We may actually try, what is a 0? Shall I add 0? 0 will be somewhere here. Of course, I should use different, okay, I don't know exactly where is the x-axis. This is the y-axis, but it's something, definitely at 1/2 we have inflection point, at 2 we have local minimum, and at -1 we have local maximum. I still don't know the exact values, right? Because I don't know, maybe a little bit higher, but we can still compute actually. Let's do it. what we need? We have to take -1 and substitute to the formula of the function. Let's maybe do it here. Okay, value at -1. And function looks like this. Okay, we will have -1/3, -1/2, +2. Okay, let's make the denominator 6. -2, -3, and 12. Am I right? -1/3, -1/2, +2. And this will be 10, 7/6. Okay, this value is 7/6. Okay, that means this will be that will be the level 7/6. Now let's substitute 1/2. Then we will have an idea. 1/2. 1/2 cube is 1/8. Then we will have 1/24. 1/2, 1/4, 1/8. And 1/2 times -2 is actually just 1. Okay, let's say 24. 1 minus 3 minus 24. Actually, is this negative number? I think it is. Let me double check. 1/2 negative, positive, negative, negative. Okay. We will have -2, -26/24. This will be -13/12. Okay, a -1 like 0.1. I mean -1 and 1/12. That means it's negative number, which means my graph should be a little bit lower. Shall we? Just to be sure. Okay, maximum. Okay, and the inflection point actually, and I hope we will be, okay, we can see just -13/12. I just lower the number just to make sure that we have good graph. And the last one is 2. Okay, that means a little bit. 2, we will have 8 cube. Yes, I'm just substituting to the value, to the formula of the function. And then 4, it will be 2 and -4. Okay, let's say 8/3, and this is -6, -18/3. It will be -10/3. Okay, makes sense, -10/3. -10/3, -13/12. Okay, we do have the graph of the function. And yeah, we don't have to, I can probably draw it some shapes, but we don't have to. Okay, that's we did the first derivative test, we did concavity test, we did find the local extreme values, local extreme values, and the inflection points. That's actually inflection point, and that's actually local minimum value. Okay, we will skip this. Okay, and as I mentioned, we do have second derivative test, but ironically, second derivative test, it is connected to concavity, but it's actually testing local extreme values. Because what we will know, as soon as we will get critical point, like C, of course, in this case, derivative is defined, then derivative at C is 0. That's how we can find C. Now, we may also compute, if it's relatively easy, because sometimes it's complicated, but if it's relatively easy, we can quickly compute the second derivative and take this formula and substitute our critical point. If this quantity is negative, then we know that function is concave down, and this will be maximum. Okay, the same thing when we have local. When we have critical point C, we can quickly compute a second derivative, substitute point C, okay, substitute the point C, and check the sign. If this is positive, this is giving us the message that function is concave upwards, and this will be local minimum. We can, of course, see local minimum, the lowest point. That's how we can use the second derivative test. The thing is, when we will get second derivative test, oh, I did kind of, oh no, I have the summary. That we can see local minimum, local maximum. The thing is, if the second derivative will give us 0 while substituting the critical number, then the second derivative test is inconclusive. We cannot really use it. Another information is that we don't have to use the second derivative test. We can always use the first derivative test. And let's come back actually to our question that we nicely did. You can see this was the first derivative test, this. Positive, negative, positive, and we can see right away local maximum and local minimum, because function is increasing, decreasing, increasing. And that's okay, that's everything. That's the first derivative test. First derivative test. We can try, okay, I will try to squeeze it, the second derivative test. We didn't use it because we don't have to, but we can try to squeeze second derivative test. Since we have the second derivative is 2x minus 1. When I take our critical point -1, second derivative at -1, 2 times -1 is -2 minus 1 is -3. This is less than 0. Less than 0 means negative, second derivative. Function is concave down. If function is concave down, at -1, we will have local maximum. This is the only conclusion, which we, of course, we knew it because we did the first derivative test. And now when I test, I don't know if I have enough room, when I will put 2 to the second derivative, 2. 2 times 2 minus 1, I believe is 3. It's positive. And we don't really use these quantities like somewhere -3 and +3. No, we don't have to use these numbers, but this is just the test. That means this is positive. We know that function will be concave up. If it's concave up, at the bottom, we have local minimum. And we did this because we used the first derivative test. That means I just wanted to show you how the second derivative test works, which of course we don't have to apply all the time. We may stick to the first derivative test because the first derivative test works always. We will skip this. We will skip. Let's investigate this question, okay? Because this one is different function, a little bit like, we can see a little bit e to the x. Actually, to have a little bit easier job, we have the graph. That we can nicely see local maximum, we can nicely see local minimum. And do we have inflection point? Because this question is not asking for the inflection point. Let's maybe try to find, or maybe it will be too difficult, but let's try. That we will have function. I can see that function is kind of like concave down, and it's I believe somewhere here, it's inflection point, and then function is concave up. And again, maybe even 0, actually, maybe even 0. Yeah, what do you think? I know that I don't have students in the classroom at the moment. Maybe this is inflection point, and then function is concave down. That means this purple dots, which we believe that's the inflection points. Let's investigate. And let's also find square root of 2 and negative square root of 2 as a critical point. That means analyze critical points. we have function 2x minus x squared times e to the x. Of course, domain are all of the real numbers. We don't have to be worried for some numbers that are not included. Okay, let's find a first derivative. Product rule. 2 minus 2x times e to the x plus 2x minus x squared and times derivative of e to the x. Nice. Let's factor out e to the x and we will have 2 minus 2x plus 2x minus x squared. E to the x and this, okay, 2 minus x squared. E to the x, square root of 2 minus x, square root of 2 plus x. Okay, and derivative is 0 if this is 0, this factor is 0, and this one is 0. Of course, e to the x is never 0, then we have no solution. This is giving me positive and respectively negative square root of 2. Of course, we see on the graph. Both of them are good, both of them are in the domain of the function. We may try to look at the test. Oh, positive. We will test the first derivative. I believe this is a good formula, good form. Okay, when I take a number, let's say 5, something greater than square root of 2. Substituting 5, square root of 2 minus 5 will give me negative number. And square root of 2 plus 5 will give me positive, but positive times negative is negative. E to the power of any number is always positive. That's when we can ignore it. Okay, negative sign. When I put 0, we will have square root of 2 times square root of 2, positive. And then when I will do, let's say, negative 5, we will have opposite, positive, negative, negative. And function is decreasing, increasing, decreasing. Local minimum, and we can see local minimum and local maximum. We did the first derivative test. We don't have to do the second derivative test, of course. Okay, we did the first derivative test, and we can see, we don't really see nicely the graph because now we have to take a function and substitute square root of 2, but looking at the graph, I know that the value is 3.4, and substituting negative square root of 2, the value is negative 1.2. And we can see this, as we have this is maximum, this is minimum. But function is definitely decreasing, increasing, decreasing. But concavity, that's what we were planning to do. Okay, let's find the second derivative because we're looking for these two purple points. We will see. I will take that form, e to the x times 2 minus x squared. And let's find the second derivative, product rule. Derivative of e to the x is e to the x times the second function plus e to the x and times derivative of 2 minus x squared okay, let's see, let's actually see we did have, okay, one more time, derivative, I mean e to the x and times derivative of 2 minus x squared, it will be negative 2x. Let's make a nice form. We will factor out e to the x, 2 minus x squared minus negative 2x, and what we actually getting, let's put negative x squared minus 2x plus 2, and hopefully we can factor out. Actually, let's put negative outside, then we will have x squared plus 2x minus 2. Now, I don't know if we can easily factor out x and x. I don't think, because this will be 2 and 1. No, we can't really factor out nicely, because -2, we have to use the quadratic formula. And let's actually, since we started, I will add the slide as always. Let's try, because I'm just interested that we do have x squared plus 2x minus 2, negative. This is the second derivative. Okay, a quadratic formula, negative b plus or minus square root of b squared 4ac over 2a. Negative b will be -2 plus or minus 4 minus 4a, and c is -2. 2a is 2. Okay, -2. 4 plus 4 times 2, 8. Okay, square root of 12. Okay, that means the numbers are, square root of 12 is 4 times 3, square root of 2 cube. Oh, no, this is still 2. And we can factor out 2. I know, looks like you probably think I am crazy, but I just wanted to find these numbers. Okay, it means one number is -2 minus square root of 3, and the other one is -2 plus square root of 3. Okay, and this one is negative, and this one is actually tiny. Oh, this one is also negative, right? Because square root of 3 is 1.7. That means both of them are negative numbers. Let's come back. That means this point will be -2 minus square root of 3. That means this one is not 0, it's somewhere here. -2, okay, -2 plus square root of 3. I will remove that dot. Oh, I can't remove it because that means this is actually the inflection point. Okay, and of course we can still test it. If I put -2 minus square root of 3, -2 plus square root of 3, and this was the derivative, the second derivative, this is minus. When I will put huge number, like let's say 100, this will be positive. Which form is, we don't have the nice form. Okay, 100, this will give me positive, e to the x is positive, but negative. This will be negative. Then if I substitute -1, I believe is between, -1 will give me, this will be still positive, negative, 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 negative and negative, positive. And then if I substitute huge negative, I will have negative number. Okay, that means this is the sign of the second derivative, and function is concave down, concave up, concave down. And when we come back, we can see concave down, of course, is not huge because I'm creating another extreme, but it's definitely concave down, concave up, and concave down. Okay, a little bit craziness with the inflection points, but they are definitely inflection point. I mean the x values where the inflection points are happening. Oh, okay, but we know the concept. I think this one will be easier, but okay, let's skip it. This one, you probably remember, we did question A and B, and I said, after covering section 4.4 about the concavity, we can answer question C. And I believe one student one student, I don't remember the name, or maybe I do, maybe I do, kind of gave us the answer. But okay, let's do this question again, because this is a nice question. Okay, we do have a graph of the first derivative. Okay, first derivative of the function. And I think I have to say that this function is continuous function, okay, everywhere on the entire interval. And now we have to find the intervals where f is increasing. Of course, function is increasing if the first derivative is positive. That means first derivative is positive here and positive here, above the x-axis. Between 6, 7, 8, between 2 and 4, and between 6, and I know that we did infinity, but let's say 9. Let's finish at 9. Okay, now local maxima and local minima. If we will quickly do the test, and we can see 0, 2, 4, 6 are the critical points. 0, 2, 4, and 6. And first derivative, below x-axis, negative. Above the x-axis, positive. Negative, positive. And now our first derivative test. Function is decreasing, increasing, decreasing, increasing. Local minimum value, local maximum value, local minimum value at 6. We can say local minimum value, it's happening at 2 and at 6, and local maximum value, it's happening at 4. Okay, that means I just repeat this. Now, what are the x-coordinates of the inflection points of the function f? I will add a slide. Oh no. Let's, perfect. Oh, okay, that means I did add the slide. Now we have to find the information about the second derivative. Okay, and we remember we kind of did this, but we were looking at the function. But what is happening if the first derivative, okay, now we have to be really careful because we're just using the tools, not really like the exact shape. Okay, that means if this function is decreasing, okay, we can see now, I believe these points will be kind of like critical points. My dots, red dots. If the curve is decreasing, its derivative, okay, its derivative, which this will be the second derivative because derivative of the derivative is a second derivative. Its derivative is negative. Now, if the curve is increasing, okay, then its derivative, which is the second derivative, is positive. And the same, decreasing, negative, increasing, oh, negative, I know I should write the negative, positive, and then decreasing, negative, and increasing, positive. Okay, we managed to get the sign of the second derivative. Perfect. Then our function is concave down, concave up, concave down, concave up, down and up. At every single x values listed on that x, on the number line, we will have inflection point. That means inflection points are at 1, at 3, 5, 7, and 8. Okay. Inflection points at, but inflection points of the function f. Okay, not f prime, not double prime, just the function f, which we don't see the graph. Okay, that we can finish this session. The most important part is knowing that if the function has the second derivative negative, then function is bounded down, concave down, of course. If the second derivative is positive, function is bended up, which means is concave up. And then we can investigate inflection points, and we also cover second derivative test, but the second derivative test is just testing the extreme values. Okay, thank you.